on this computer. Okay, so I think we're cooking now. Sorry about the delay. The room I was intending to go in, even though it's right across the hall from us here, is not available, but this room seems fine with just a little bit of extra stuff, so we're okay. But in any case, let's kind of get started. Everybody saw I had sent a couple emails yesterday. You got those emails. There is a tech talk coming up that I emailed you about, as well as a hackathon. I encourage all of you to get involved with those things. I think they're all available online. I know this semester is a little bit funky, right? But in any case, strongly encourage you to do this. You know, I know some of you have limited computer programming background. So with those folks in mind, you know, you're going to have to put in some extra effort in this class. I do encourage people to work in groups, and I'll mention that many times. But keep in mind that if you're going to work with people to get your homework done, that's fine, but you're going to still be writing your exam yourself. Okay, so, you know, operate as a student who's trying to learn, not somebody who's just trying to get their homework done. All right, because in here, I'll just open up the keynote here real quick. And everybody online can see my screen shared, right? Okay. This class is programming language theory. So in here, we're going to be writing a computer programming language. All right. So it would make sense that if you have limited or rusty computer programming skills, and the fact that we're creating a programming language in here, that you're going to have to play some catch up, right? You know, so as grad students, the idea is that, you know, you already know how to learn. So anything that you didn't walk through the door with today, you're going to be able to figure out between now and the end of the semester, with the understanding that you might have to spend some significant extra time outside of class to catch up on these things. It just is what it is, and you know, that's the price you pay, I guess, for kind of switching careers or coming into a little bit different background. But I'll give you plenty of examples. We'll write a lot of code in class, but then I also encourage you to work with your classmates on the homework assignments, that kind of stuff. So grades in the class, pretty simple: 60% homework, 40% final exam. We'll only have one exam. It'll be at the end because we don't have enough time to have multiple exams. So basically everything that we're doing homework-wise will prepare you for that final exam. Okay, so questions about the breakdown of the course? Pretty straightforward, right? All right, and this stuff's on the syllabus, the normal grading scale, 90, 80, 70, 60. Let's see, so the Blackboard's open. In this class, we're going to be using several tools for communication. Some of you are already on those things. I'll go ahead and, well, here, I'll just write it in here. So on the Blackboard, we have links to all these things, but we're going to say tools class. So these are things that you'll need to have, and I also put these in that email I sent you. Okay, so one we'll be using in here, I'm going to probably, all my examples will be using Eclipse for Java developers. I actually gave you a link directly to the download for Eclipse for Java developers, because the new way Eclipse works is you download the Eclipse client and then you select packages from that. You can do that, no problem. That's the way I do it on my computer, but specifically you want the package for Java developers, not Java Enterprise, not C++, Java developers, because we're going to be using the Java programming language in here to do our stuff. So I gave you a link directly to an installer that brings the Java thing. I don't care if you use a Mac, a PC, Linux, all those things are, that's kind of the reason I picked Java in here, because our focus in this class is the focus on language building, not necessarily on other aspects of IT. All right, so I wanted to be platform independent, so I didn't have to manage a whole bunch of crap. So all these tools are available for all the different platforms. So we'll be using Eclipse. We'll also be using GitHub. What is GitHub? How many of you have used GitHub before? Or at least have downloaded something from GitHub at some point? Usually that's your first experience, right? You don't interact with GitHub yourself. It's somebody gives you a link and says, go and download something from GitHub, right? So what is GitHub? GitHub uses a technology called Git, which is, let's call it source code management software. And GitHub, so Git is the underlying technology. GitHub is an online repository for Git repos. So the idea is you create a local repository on your computer. And then when you want to be able to share that with other people, i.e. me, when you turn in your homework assignments, or with your classmates if you're working collaboratively on things. I actually want to reiterate that aspect of things again here, because my classes are a little unique in that. So some of your other grad classes, historically, because of the culture that some of our grad students come from, this idea of working together is pretty common, right? Collaborating on things and stuff like that, where in the United States, it isn't necessarily that common. So you've had teachers, accuse you of cheating and, things like that. So when I do this stuff in my class, I'm giving you permission to do that. Okay, this doesn't mean all your classes are going to work this way. So make sure that when you're in a different class with a different professor, unless they say you can work in groups or collaborate on your homework assignments, assume you can't. So you shouldn't be turning in the same homework assignment because they'll get mad at you and give you bad grades, and that's bad, right? Okay, in my classes, you can collaborate on everything except the exam. Okay, so I'm going to find out on the exam if you suck. Okay, and as you see here, the exam's worth a lot. All right, so I view learning as kind of like a video game, okay, or a sport. Okay, maybe sport's the better example. So learning is kind of like a sport where so I'm guessing several of you are cricket players. Then maybe soccer or football in your country, maybe. Okay, ping pong. Total cultural stereotype too. I also know played well. Okay, but in any case, when you first picked up one of these sports, when you first started doing it, you sucked at it, right? You weren't any good. What did you have to do? You had to practice. And what were you practicing for? You were practicing for the big game. When you actually had to put your practice into practice, right? So the idea is that when you showed up to practice for your sport and you did a bunch of stuff, you were supposed to fall over. You were supposed to trip. You were supposed to hit it poorly, whatever it is. Those are the things that happen during practice. All right, so the idea here is that the 60% of your grade, that's homework, I'm not going to necessarily grade that with this fine-tooth comb. I'm more interested in the effort you put into it, the things that you tried while you were doing it that didn't work, because that's where learning is taking place, right? Okay, and so I care less about the final solution. That doesn't mean I don't want you to come up with a good final solution, but that's where I encourage you to work with your classmates to get a final solution that is reasonable, but it's not about the final solution. It's about the path to getting that solution, because that's where your learning is taking place, okay? I will be picky on this final exam when you get to show me that you were ready for the big game. That makes sense? Now, the final exam will be written in such a way that it should be reasonable, given the time, how much time you have available and the kind of material I'm asking you to come up with off the top of your head. But it's all going to be problem solving. I won't have like multiple choice, true, false stuff. So the idea is that the homework assignments will prepare you for that final exam. So if you're getting out of the assignments what you should be getting out of, you'll do well in the final. If you're not, you're letting one of your other classmates do all the work for you. You'll do well in your homework assignments, you'll bomb the final exam, and what will you have in the class? You'll have a 60%. I don't think any of you want a 60% in your, in the class, right? Maybe I give you a D- for that. Still not good, right? Okay, so class is set up for you to succeed, but you have to do the work to succeed. Make sense? But again, I want to reiterate that that's how I run my classes. Don't necessarily assume that the other teachers work that way, okay? Because like I said, we've had issues in the past with, plagiarism and stuff like that. I get paid either way. You're only hurting yourself if, if you do that junk, and I'm not going to sit here and police it, is the punchline. All right, any questions on any of that?
What is the form of the assignment?
Well, it'll probably be online on Blackboard, but a majority, and we'll talk about it in more detail once we get closer to it, and I've really thought through it, but the exam will be it'll probably be half programming and then half looking at code and telling me, what does this do? Or maybe there'll be a kind of an SAE question, like, given these pieces of information, how would you solve this problem? Explain to me how you would solve this problem, something like that. So a good mix of, practice, theory, and then I want to see kind of your real-time problem solving. But there won't be any true, false, or multiple choice. I don't believe in that stuff. And I want to know what you know. So on the exam questions, there might be several correct answers, but there'll definitely be a bunch of incorrect ones. Okay. All right. Any other
question?
Yep, go ahead.
How much programming is involved total? And that's like another theoretical class this much. So how
Are
much?
you talking about on the final exam, or are you talking about
all over? How much practical things are involved?
Well, there'll be a lot of programming, but hopefully I give you enough examples that you'll be writing the code in the context of kind of what I've already given you. That doesn't mean you don't need to know how to program. You don't need to be able to learn stuff on your own. As part of the maturity that you should have as a grad student, is even when you don't know something, you should be able to learn it relatively quickly. But this class will be less about coming up with solutions to programming on your own, and more about how do I create a tool that allows human beings to talk to a computer. And that's what we'll be talking about today. So I don't want to mislead you and say you won't need to program. You're going to program on every assignment. But hopefully that programming comes in the context of I've given you enough information for you to at least have a starting point that you can operate within, and you only really need to write code that is similar to the code I've already written in class or something like that. So you should be able to get up to speed on your own. The focus is on creating a tool that lets us communicate with the computer, not write, some mobile application or something like that. Even though ultimately we are writing a tool that is software based, and it's not easy. But that's kind of the other class. CSC518 is a more programming, problem solve, algorithms based class. And then the online class that I'm offering this semester is 560. So whether you take it online or you take it face-to-face with me in the future, that's a RESTful API class that, yes, relies on programming, but I teach you tools from the get-go. So we look at what's called the mean stack in there, which is MongoDB, Express Web Server, Angular, and Node.js. And we look at each of those in turn through tutorials and then create our own APIs using those things. So again, it doesn't require you to have a background in those things, but it does require you to have a maturity in learning. So when you go through your undergrad degree and then you go and have some work experience, whatever it is, it's not so much what did you learn, it's you learned to learn, if that makes sense. I like a good example for this is there's a company, it's probably one of my favorite companies in this area, and that company is called Acuity. It's up in Sheboygan, and they tend to hire our top undergraduate students. What I really admire about Acuity is they are not looking for you to walk in day one with all this knowledge that you can immediately become a productivity unit for them. Instead, what they're saying is they expect that you got this degree, you proved, through your GPA and crap like that, oh, this person knows how to play the game. They know how to get instructions and solve problems and keep their grades, reasonably well by kind of playing the game. But their assumption is you've learned how to learn. Because what they do is they invest in you. The first 3 months you're at Acuity, you're not doing any productivity work. They have like a 3-month boot camp they put you through, teaching you the Acuity way of doing all these different things you're going to have to do for your actual job. So it's like more college. Does that make sense? You show up to work and they're paying you to learn their way of doing things in the context of some of the stuff you already know, but then your ability to learn from there. Okay, so that's the assumption I make for all of the grad students is, when I have a freshman undergrad student, a CSC549 first semester programming student who has, no background in computer programming, my assumption is that they also are fairly weak in being able to teach themselves and stuff like that because they're immature, right? Their background is learning from high school, right? But all of you have an undergrad degree. You've already gone through that. So I expect at the very least, you know how to learn. You know how to teach yourself. And, that's not always the case. Sometimes you are really, really good at copying off other people. I don't care. It's fine. You're only hurting yourself. Like I said, I get paid either way, and you're spending a bunch of money to come get a master's degree and, you can get that degree, learn nothing, and then go and get fired from every job. So, you get to choose what you're going to do with it, right? But my expectation of all of you, regardless of your background in computer science or programming, whatever it is that you're mature enough in teaching yourself, you know how to learn. You can use web resources, things like that. You can collaborate with each other and help each other learn, stuff like that. Make sense? All right, so this was all kind of a long-winded answer to how much programming there's going to be. There's going to be plenty of programming, but I'm not going to ask you to invest. I'm not assuming that all of you are, programming gurus who have been working in industry for 10 years writing software. I'm going to give you the tools you need. I'll write a lot of code in class so you see kind of the process. And then the expectation will be for you to close the gap between where your current skill set is and what that skill set needs to be to do the homework. Okay? That's the extra work you'll have to do because you know how to learn. Got it? Okay. Any other questions before we dive into content? I see a chat. Is there another? Well, the question is will it deal with core Java versus advanced Java? I guess I would say core Java. My interpretation of what you're asking here is, are we going to be using a lot of built-in tools that are part of, Java's larger tool collection? I would say no. And part of that is not that I want to discourage you from using those things in your career, but we're focusing on the mechanics of language development in here. So I want us to work with the simplest tool set possible and build our tools out of that. So kind of like you got a Lego set and everything starts with the basic Legos. So again, I'm not teaching you basic Java in here. I'm going to assume that one way or another, you're going to learn the tools that you need to do your homework. All right. I'm making no assumptions. I'm going to write code as if you can read it. And if you can't read it, you're going to have to figure out how to read it. Okay. And I'll explain stuff if you ask questions, but the idea here is that I'm going to be doing these things in the context of what I think is what you're asking here, is the basics of Java, core Java, the part of Java that looks like every other C-based programming language. Not some weird built-in library that allows Java to accomplish something magical because somebody else already did 94% of the work. That makes sense? So I'm guessing that's what you're asking. So this is not going to be learning some magical Java tools. Our focus here is creating a tool for communicating with a computer. Okay, there'll be a lot of string manipulation, because we're going to have to we'll talk about this more here in a few minutes, but we're going to have to take our syntax, the things we want to say, as a human, and we're gonna have to turn it into something that this guy can understand. All right, make sense? Okay, other questions? We get them out of the way before we dive in. Go on. Yep.
Homework will be like on a weekly basis or bi-weekly, something like that?
I would say there's a pretty good chance of a homework every single class. With the idea that the larger homework assignment will be the Wednesday one that's not due to the following Monday. Yeah, so I mean, I probably won't give you something that'll break your back from Monday to Wednesday. Monday to Wednesday might be kind of the setup, or the take what I did in class today and enhance it a little bit, something like that. So you're kind of getting those reps in, and then I'll give you a little bit more meat to chew on when you have a little bit more time. That seem reasonable? Say this again? Oh, like the Bible stuff? I'm not having them in this class. But I think I even put it in one of my emails, didn't I? That because all these classes are also offered online, this is kind of against my personal belief, but historically what I have in all my classes, for those of you who haven't had me before, is every week I have you read a chapter out of the Bible and then reflect on it. Understand that I recognize that not all of you are necessarily Christian, but also you should recognize that this is a Christian university. Okay, so it's a two-way street. So part of my angle might be that, hey, I'd like you to learn a little bit about the Bible, and my belief is that God will do the rest of the work, and maybe change your perspective. So what I'll officially say is I strongly encourage you to pick a book out of the New Testament in the Bible. I would pick one of the Gospels. If you haven't read one of the Gospels before, those are one of the first 4 books. The book of Luke is a good one because the guy is a doctor, so he's more of a logical person. So maybe for a computer scientist, if you haven't gone through one of the Gospels of Jesus before, the book of Luke is a good one. Read a chapter or 2 a week and just reflect on it. I know some of you are going to be reading this like it's a fictional story, and that's fine. My feeling is if I put it in front of you, God will do the rest. But I'm not making it part of the actual homework assignments because it's part of the online learning thing, that they didn't want that to be part of the graded material. And I want to make sure that what we're doing here face-to-face is compatible with what we'll do in the online version of the class. Make sense? So I'm guessing most of you will ignore what I just said, but I really encourage you not to ignore it. Take it upon yourself, read the Bible, give yourself a little bit of time, see what it's all about, that type of thing. But it won't be something you have to do on a weekly basis. Got it? Okay, so let's dive in here. So we'll be using Eclipse, we'll be using GitHub, and I'll go through the process of GitHub today. In fact, your assignment for Wednesday will probably be to do something with GitHub and ultimately submit for me some code using GitHub that is an example that, okay, I can do my homework. I know how to use the tools to do my homework. That makes sense? So I'll actually demonstrate for you today exactly what I want you to do for your homework. And then what I'll expect you to do for Wednesday is mimic that, so that I can now give a thumbs up that every single one of you knows how to use GitHub and knows how to turn your homework in. Make some sense? Okay. Let's see, what else we'll be using here. I know several of you are already on here, so I use Slack for communication. So Slack is cuwcs.slack.com. If you don't already have an account, go there and you can sign up with your cuw.edu email address, and that'll let you in. If for some reason it's not letting you in, or if you have a CUAA Ann Arbor email address, you'll have to message me and I'll send you a link directly to invite you to it, because it only automatically lets you in if you're signing up with a CUW edu address. But anyways, Slack is the tool, so I'll just show you what it looks like here. This is the tool that I'll use for communicating. So you see here that Josh over in Ann Arbor, he's already put out there that, said, hey, I'm on Zoom, blah, blah, blah. Blade's on here. In any case, any announcements I'll make for class, I will put here on Slack. I will not always send an email. Okay, Slack is convenient for me. Email requires me to go into Blackboard and go to send email and all this junk. So I expect all of you are checking Slack multiple times a day. You probably should just put it on your smartphone and set up notifications for our class so it buzzes you just like you got a text message. Make sense? So my suggestion is if you have questions about something in the class, something you're working on your homework, something like that, you post it in the 549 channel in Slack so that when you so that maybe one of your classmates answers it before I do, and you don't have to wait very long to get help. Also, if you're going to get together to work on your assignments, maybe you say, hey, I'm going to be working on this in this Zoom channel at such and such time tonight. If you want to pop in, so if we have questions, we can ask each other, stuff like that. Whatever you want to do, but this is my main communication tool that I use for my classes. Okay, and several of the other profs use Slack as well. Okay, so that's our Slack channel. Let's see, anything else I want to talk about? I think that's it for the tools that we'll use. Something else pops up, I'll mention it. All right, so let's get rolling. So, and these are things, if you had my classes before, some of these slides might be review, but one of the things that several of you have had, actually most of you had Dr. Locklear this last semester, right? So Dr. Locklear and I have been working together for years and years and years, and very rarely do we agree with each other. It's pretty kind of a funny love-hate relationship. I think we both respect each other a lot. We just have different perspectives on things. But this is so when we do agree with each other, it's usually gold. It's usually something that I think is pretty important. So one thing that Dr. Locklear is a big advocate of is this idea of something he refers to as the grand ideas of computer science. I'm guessing he referred to it in his class at some point, multiple times, something like that. Which is, and the generalistic concept of this is that it doesn't matter which area of computer science you're in, they all relate to each other. There's these core concepts that everything in computer science has in common, all right? So I 100% agree with this. And one of the things that I try to do in my classes is you'll see some of my classes will have these same topics at the beginning. And then we start looking at those through the lens of whatever the subject we're working with is, okay? So with that being said, the fact that he believes that and I believe that probably means it's important. is the kind of the punchline. All right. So with this in mind, I teach a lot of our programming classes, and I like to kind of start off with this concept of remember that we're human beings. We have an entire lifetime of experience solving problems with other human beings. In fact, we're great problem solvers, right? God made us to be great problem solvers. And with this in mind, we're so good at solving problems, sometimes we take for granted how good we are. The example I often use is, you see students walking down the hall, texting while they're walking, they're bobbing and weaving in and out of people, they don't bump into any walls, none of this stuff. They're communicating with other people electronically, they're dodging traffic in real time, they're not falling over while they're walking. All of these things they're doing and not even paying attention, right? We are amazing problem solvers, but the thing is that we're so good that we have trouble articulating how we solve problems. Now that's where computer programming is difficult. That's why it's difficult for us, because we're used to expressing ourselves, solving problems with human beings. Well, now we need to tell a computer what to do. And now we're dealing at a level a little bit lower. So so kind of like the traditional IT world, you're typically interfacing with pieces of software that have already been written. If I put any piece of software in front of you that has a file menu, right? You pretty much know, well, if I want to save something, I click on the file menu, it drops down, I go and do some file saving stuff. And you can make a pretty good guess at any piece of software I put in front of you because you're used to using software, right? You've been trained in how to use kind of software-based tools. So the same thing is true for a lot of areas of IT where there's different tools and these tools do different things, but they all kind of behave similarly in terms of how you interface with them. And that's kind of what the human computer interaction class is about, the 820 or 520 class. Was that this last semester as well? Yeah. So, that class kind of talked about how do you interface with the computer. Now, I think that subject is kind of a boring subject, but it doesn't mean it's an unimportant subject, right? Because that's almost something that you take for granted because like, I've been using Windows or Mac or whatever for years and years and years and years. It doesn't matter what software I just downloaded. I could probably figure out how to use it pretty quickly because I already have this skill of interfacing with it, right? So as human beings, we already have this skill of interfacing with other human beings, right? We've been doing it our whole life. In fact, we have now forgotten how we do it. We just do it. Many of you maybe drive cars, so you already have the skill of driving a car. You've practiced, and now it's just kind of automatic, right? You hit your turn signals. You don't think about, well, do I push it down or up for a different turn? You just do it because you've done it so many times, right? It's like muscle memory. All right, so whenever we've practiced something, we've had to adapt our problem-solving skills to whatever is the demands of that particular problem we're solving. And human beings are very good at this, but once we master something, we kind of forget what it took to master it. We have trouble explaining to somebody else how to do it. If you kind of think about this, one example I often use is the idea of walking. But walking is so complex that it's like impossible for us to explain all the muscles that are involved in walking. But think about maybe driving. When you're sitting there, so I've been driving longer than most of you, but many of you have been driving for a while, right? Multiple years at this point. So one thing you maybe next time you get in the car, you try to notice that you have this little pattern where you're checking this mirror, you're checking that mirror, you're checking that mirror. You don't even think about it. Right? You have this system that you've practiced that you want to be aware of kind of what's going on around the vehicle. And because you've done it so many times, you don't think, check this mirror, then check that mirror, then check that mirror, then check that. You don't think about doing it. You just kind of passively, loop around and look at the mirrors and kind of get a good idea of what's going on around you and that kind of stuff, right? And then what kind of becomes interesting about that is now technology is helping us cheat, right? When you back up a car, how many of you have a car that does not have a backup camera? I'm guessing several of you, right? A lot of times, students, you get a car that drives, it rolls. You're not going to spend extra on a vehicle. You're on a budget, okay? So older vehicles do not have one of those backup cameras. Know what I'm talking about? Okay. So what did you have to do when you're driving a car that does not have a backup camera? You had to get that skill of kind of knowing, well, how close am I to the car behind me? You had to, based on like looking at your mirror and kind of seeing like roughly how close I am. And usually you think you're closer than you actually are. Right? That's why you see people, pulling in and out multiple times. They're like, look, you could have just done it. You had room. Okay, but they're having to operate with less technology, right? So you build this skill of being able to, back up. Well, once you have one of those cameras, especially if you've had the camera for a long time, you lose that skill. You stop practicing that skill. Camera does all in my car. When I back up, I have this giant screen. It shows me everything that's going on. It does all sorts of beeping and stuff if I'm getting too close to stuff. And mine has 360 degrees of stuff. It beeps all over the place. Goes super crazy inside of a car wash. Yeah, you got stuff hitting it from all sides. Okay, but so what has that done? I'm no longer trained to look behind me when I back out, even looking for cross traffic. Because my car has this, I don't know what the technology is, radar, LiDAR, sonar, whatever, some kind of technology that as I start backing out, it's looking for cars on either side and it will beep at me So I stop backing out. So I don't even have to look for traffic. I just have to put it in reverse and just inch back, and it'll tell me whether I'm good to keep going. So what happens when I travel and I get a rental car? Oh my gosh, all my bells and whistles are gone, right? Same thing. How many of you have one of those blind spot lights on your car? Where, because when a car gets too close next to you, you can't actually see it in your mirror, right? You got the little trick where you can lean forward and create a different angle with your mirror, and you can see it. Otherwise, what do they train you? They train you to look back like that to see your blind spot. Well, my car has sensors. If somebody's in my blind spot, I get this little orange dot on my mirror. So I can just glance there. It's like, oh, nobody's there. I can change lanes. Then I go and get a rental car that doesn't have one of those. Right? So I've become accustomed to driving this technological vehicle that has all of these things in it that have gotten me out of practice at doing some other things, where it takes me like, a day when I get in a rental car to kind of remember that, oh, these are some things I need to do in order to safely navigate the world. Okay? So technology tends to do a lot of the work for us, and before long, we're going to have self-driving cars, right? We're not going to do any of the work. It's just going to take us around. You view a long road trip as an opportunity to binge watch some Netflix show or something like that. But in any case, human beings are really strong problem solvers, but we do struggle with articulating how we solve problems because we're so good at it, or because of how used to something we get where we don't even think about it. Okay, and really that is a God-given talent where we are so special that we can do those kinds of things. Okay, computers aren't like that. Computers are dumb. You got to tell them every tiny little step that they have to do to accomplish stuff. That's not in our wheelhouse. We're not good at that. We're not, if I told you to tell me how to drive, you would leave huge swaths of information out because these are things you just take for granted. Make some sense? So the thing that we're solving in this class is the idea of we already are good problem solvers. We're already used to solving problems with other human beings, but now we have to create a tool for a human to tell a computer what to do. And in order to start doing that, we have to think about how do human beings solve problems, in kind of a simplified term. So I say that we use our memory, we ask a lot of questions, and we perform repetition. We can sit here for a week and probably come up with, a longer, more granular list or something like that, but I think this kind of captures it, right? We have to remember things. That's an important part. You can't solve a problem unless you remember the problem you're trying to solve. And sometimes we need pieces of information that we need to remember. If I'm going to call a phone and call somebody, I need to know who I'm calling and maybe what their number is, that kind of stuff. All right, so we rely on our memory a lot. We ask a whole lot of questions. When you're walking down the hall, you're saying, am I going to hit somebody? Am I going to hit somebody? Do I need to dodge left? Do I need to dodge right? We're asking constant questions. We're asking so many questions that we don't even recognize we're asking them. Right? If I'm going to change lanes in a car, I hit my left turn signal maybe, I glance at my blind spot, and then I just go. Some questions were being asked in there, even though I didn't think that I was asking a question. Make some sense? All right, so we're constantly querying our senses, querying the world around us using, video, audio, whatever it is. Okay? And then we do a lot of repetition. Once we have patterns that we have found work, we can often use those patterns to, in repetition, to continue to solve problems. Make sense? Okay. So this is how a human being solves their real world problems. We've gotten really, really good at leveraging these things with the stuff that we're practiced with. So we've been dealing with human beings since we were 0, right? We've been driving cars since we were 16, 17, whatever the age was, and now you've gotten pretty good at that. So as we practice stuff, it becomes very natural for us, okay? But this is how we apply. This is what we apply to all of our problem solving. And we want to remember that as we start thinking about telling a computer what to do. Because even if you do have an experience with programming and you've told a computer what to do, it's still going to be something that you're not as practiced at as walking, or probably driving a car, or interfacing with other human beings. We have lots of practice with those things. Okay. So what's the job of a programming language? It's to tell a computer what to do. Done, right? If I want you to go fill up a glass of water, with a human being, I have a natural language, right? I could say, go and fill up, here's a cup, can you go fill it up with water? That gives you the information to know what I'm asking you to do, okay? And think about all the steps that were left out there. I didn't tell you where to go to get water. Most of you have been around this area enough where you kind of know, well, if you go that way, there's a water fountain you could fill it up with. There's another one kind of this way, but it's a little bit farther away. So I don't care where you fill it, just go fill it. So I'm relying on that other person to be able to fill in some of those blanks, right? We're already good at that. We're already good at telling humans what to do. And we have protocols, languages for accomplishing that, right? So the language I know is English. Most of you in here know English, and you also know other languages, right? It's always fascinated me. I visited India a couple of years ago, and it's fascinating how you can be in one town and people speak like 6 different languages because of how the languages are broken down in the country. And you get in these big cities, people have come from all sorts of different places, and I imagine from a human being perspective, when 2 people meet each other in India, they have to figure out what's their common language. Which is kind of interesting. We're in the United States. You go to any state, the common language is English, but you might just have an accent or something like that. Or sometimes you use certain words, like the joke is in Wisconsin versus. So I grew up in Illinois, which is the state just south of here, where Chicago is, and. So in Illinois, we call Coke, soda, we call it pop. In Wisconsin, we call it soda. In Texas, they call any kind of soda, they call Coke. So if you say, I'll have a Coke, they'll say, what kind? Sprite. You know what I'm saying? Okay. And so that's just one example. We have all sorts of other weird things and stuff like that. But, so you have those changes between states, little idiosyncrasies, but not whole new languages. All right. So the way humans talk to other humans is through these natural languages, which are incredibly powerful and also incredibly nuanced. When you think about, English or whatever other languages you can be very, very expressive with those languages and expect a human being to read between the lines. Because with humans communicating with each other, it's more than just what we're saying. We also use facial expressions, and you've heard sometimes you text somebody something, and because they didn't see you say it, they just read the words, they take it the wrong way, or they don't get you were joking or something like that. Okay, because when humans talk to other humans, we're using a whole bunch of different things: hand gestures, eye expressions, tones of our voice, loud, soft, whatever it is. Okay, these are really powerful languages, right? Programming should be easy. The programming languages we use are so simple compared to the natural languages that we're used to. But why do we perceive that computer programming is hard? Well, we've been speaking English for a bunch of years. We've been speaking Telugu or Chinese or whatever, pick your native language. Pick your favorite natural language. You've been speaking it for years and years and years and years. You don't think about it. You just say it. Make sense? We haven't been telling a computer what to do for that long. And even for the amount of time we've been telling computers what to do, we have only practiced certain ways of communicating with the computer for 8 weeks at a time or 16 weeks at a time, something like that. And all along, what's also happened? The computers change, right? They get faster, they get more memory, the software changes, the tools that are there for us change. I mean, you just had this artificial intelligence class, and in there, hopefully you kind of saw that, if you would have had an AI class 15 years ago, You would have talked about the same topics, but you wouldn't have had some of the tools that exist today for performing some of those things. You would have had to create the tools on your own. So now more and more stuff is available to us where you can have somebody, and we see it even with computer programming. We're going to be using Java in here. We're going to be using a tool called Eclipse, where you write your code and you hit a little play button and it runs. Something's happening behind the scenes there. That code is getting compiled. Then it's getting run through the Java virtual machine, the interpreter for Java. These are things that are occurring, but you're not aware of it because you've been blessed by being able to use this great piece of software where you just write it, even puts little red squigglies under bad stuff. When you mess up, it highlights it and say something's bad and something bad is here. So you get all these benefits, and it's because the computer that we're communicating with is this constant moving target. And what is it trying to do? It's trying to become easier and easier and easier for us to interface with. So grandma or grandpa can use a computer, right? I have one living grandparent. She's very old, and she has an iPhone. And she loves it. She plays her games on there and all sorts of stuff. Well, computer science didn't exist when grandma was in school. Okay, so she had to learn computers after she was 80. That's when she was first introduced to computers, as post 80 years old. So you imagine for a computer to be able to be interfaceable for somebody like that, that's where human-computer interaction comes in, right? We need to make it friendly for her. Now, do you think an operating system needs to be friendlier for my grandma or friendlier for any of you? You could figure out a more complex system, right? Okay, you grew up with technology, all these things. Grandma didn't. But you still, how many of you have iPhones in here? A couple of you. How many of you have Android phones in here? The rest of you, right? So either one of those, I could teach grandma to use, right? They're friendly. You use the same tool, right? Because that's the tool that's put in front of you. So as modern day practitioners of using technology, we are getting farther and farther from the nuts and bolts, the things that are happening under the hood, which means that you are missing knowledge that you're capable of learning. You were just never forced to learn it because you entered into the technology world at a point in time when some of those problems had already been solved for you. You don't have to know how cars work in order to drive a car, right? Where in the early days of automobiles, you probably did. And the same thing's true now, like with boats. If you own a boat, you kind of need to have a little bit of knowledge about how boat motors and stuff works, just in case you get weird. They're not as reliable as cars are. They're close, but not as. So you have to have some knowledge in case you have an issue, right? With a car, you just dial a phone number. My car broke down. They come and tow you away and go and fix it. And you give them money. Now you have a working car again. You didn't have to know anything about how that car worked. Okay? So this is kind of our cyclic problem we have with learning how to problem solve with computers, is because the computers are constantly changing. Humans are not, right? The way a human being thinks today is the same way a human being thought when you were 1. So 22, 23 years ago, whatever it is, human beings are still the same, right? The only differences in us is that we've gotten used to being reliant on more and more technology, but we still think the same, okay? And that's kind of more and more evident today with COVID, right? Now that we're like locked in houses and stuff like that, we realize some of those things that we missed, that we took for granted before, time with friends and family and things like that, where it's like, I'll call mom later, or I'll go hang out with Bill later. Where now it's like, oh, I haven't seen Bill in months. So, we take for granted some of those things until they're missing. All right, but go ahead.
Why you only mention what to do but not how to do?
Which part?
A programming language not telling the computer how to do.
Well, that's what the whole class is about, is that part of it.
No, what I mean is your statement, the talk of a programming language allow him to tell the computer what to do, but you didn't mention how to do.
Wait a second, if you're telling now the student to say.
I get what you're saying, yeah. So the idea here is, and I mean, we talked about it, is if I tell you what to do, fill my water, I'm expecting that you'll figure out how to do it, right? Where the programming language, so I'm expecting intelligence, right? On that side, that's the stuff from your AI class you just had, right? I'm expecting intelligence on your side that you'll figure it out. Where with the computer, not only do I have to, I mean, the means by which I tell it what I want to do is by telling it how to do it. So really, I'm still telling it what to do. I'm saying, add 1 to this number. Then I'm saying, do this 10 times. Then I'm saying, so the what I'm telling a computer what to do are far simpler things, right? If I told any of you to put your hand up and then wiggle your thumb like this, you would think that I was crazy. Like, oh, okay, here you go. Why am I doing that? Well, I'm just preparing you for picking up this cup, right? So I got my hand up. Now I'm going to move my elbow here. Now I'm near my soda cup. Now I'm going to curl my fingers, all of them, all 4 of these fingers, maybe one at a time, and then I'll clutch my thumb. I'll squeeze a little bit, and then I can lift it. Now I have something. So I didn't tell the computer to grab. I told the computer to do one movement, followed by another movement, followed by another movement. So I'm still telling the computer what to do. I just have to break it down into those baby steps. Where the way we talk to humans is just say, hey, go fill my water. And we rely on the intelligence on the other end to figure it out. Does that make some sense? So I still would stand by the statement saying we are telling a computer what to do, just the what is far less interesting than we might tell a human, right? Okay, so that's ultimately the job of the tool that we're going to be creating in here. Tell a computer what to do. All right, so we already talked about this. I mean, I kind of gave myself some starting points, but I get off on my own tangent. So we already talked about how humans communicate. So the job of a programming language. Ultimately, it's so we can tell a computer what to do, but when a human being is the one inventing the language, like we're going to be doing in here, what's the job of the programming language? We are lazy. Now, I don't really say that in a derogatory way. Human beings can be lazy, right? I don't have to check my blind spot in my car. I just glance at the orange light. If it's on, don't go there. If it's not on, lane's clear, no problem, okay? We've been trained into becoming lazier and lazier because of the technology that's around us. So with all those things in mind, it seems reasonable to say that a human being is not really willing to drop down to the level of a computer and tell a computer what to do in terms of zeros and ones. Now, from a computer science perspective, like when you take the mobile computer architecture class, the 548 class, it's interesting for us to go and learn that stuff, right? Because as computer scientists, we should know how the car works, right? But you don't need to know how the car works in order to drive the car. You don't need to know how a computer works in order to use a computer. But computer scientists should understand those things. That's why we're going to be the professionals in this, right? All right. So it's interesting for us to go and learn that side of the equation, to get down to the zeros and ones level. But we can still say that as a human, we don't really have an interest of speaking binary to a computer on a daily basis. It's more of a magic trick we pull out every now and then to show how smart we are, right? How much we actually know. But at the end of the day, what we really want is we want a tool that allows us to still maintain our humanity, but still tell this computer what to do. Make sense? We want both and. The old saying, we want our cake and we want to eat it too, type thing. So we want to still talk to a computer kind of like it's a human. And then let the tool that we build translate that into those zeros and ones that the computer ultimately needs to operate off of. Okay? So allow a human to communicate with a computer in a way similar to how we already communicate with humans. So this implies that the language does most of the work for us. This isn't a 50-50 thing. We're not meeting each other in the middle. That's human fairness. We don't need to be fair to a computer, right? We're more important than computers are. You know, humans hate it when one human says they're more important than another human, right? That's not fair. You know, we're all created equal. We're all created in God's image. Okay, humans are humans, and we're equal partners in solving problems. But we're not equal with computers, right? Now, we're better than they are. They just make our lives easier because they do tedious work that we don't want to do. All right? So we're perfect, our conscience is perfectly fine going to bed at night knowing that the computer's doing 99% of the work and we're only bringing 1% of the weirdness to the table with whatever programming language we've created. Make sense? So that's the job of our programming language. It's still a power tool that benefits the human being. All right, so I mentioned before that human beings solve problems with memory, asking questions, and repetition. With that in mind, 100% of programming languages will have facilities for these three things. My argument would be it's not a programming language if it doesn't have facilities for these three things. That doesn't mean it's a bad tool. You know, the example I typically use is like HTML. When I ask a group of students, you know, what programming languages do you know? HTML is almost always one of the things they mention. HTML is not a programming language. You can't create variables, you can't remember stuff with HTML. You can't ask questions, you can't write loops. That doesn't mean HTML is a garbage tool. It's a really important tool. Okay, it's a data representation language. It allows us to express to a web browser how we want pretty pictures and text to show up. That's important stuff, but it's not a programming language, right? Because it's not mimicking these ways that human beings solve problems. So 100% of programming languages will have a facility for memory, usually called variables. It'll have a facility for asking questions, usually conditionals or switch statements. It'll have a facility for repetition, loops and functions, methods, subroutines, procedures, whatever you want to call them. All right. These things are things that every single programming language must have in order for it to be considered a programming language. That isn't to say that programming languages are better tools than data representation languages. They are different tools. Sometimes you need a chainsaw, sometimes you need a hammer. Both tools are important, right? They're just different tools. All right, make some sense? All right, so that's the mapping when we think about the programming language version of how human beings already solve problems. All right, so I want to spend a few minutes talking about the CPU. And again, this goes back to that grand ideas of computer science stuff. For those of you who take the mobile computer architecture classes, I think is that next semester? Yeah, with me. We're going to have the same slide. We'll have the same conversation again, but I'll angle it from that subject matter, right? Because in here, we're not talking about the hardware registers and the caches, L1, L2, L3 cache. We're not talking about all that stuff. In here, we're talking about a programming language. But at the end of the day, when we write our programming language, what are we doing? We are telling a computer what to do. And what's the brain of the computer? You know, you ask somebody, what's the CPU? That's usually their response, right? It's the brain of the computer. But whatever, that's good enough. But ultimately, what does the CPU do? You feed it some zeros and ones, and those zeros and ones correspond to one of the many things that CPU knows how to do. Make sense? So here, we'll all do the exercise. I just did it a few minutes ago. We'll do it again. It'll give us a good workout. Everybody put their hand up. Hand up. Oh, it's hiding behind. Drop and give me 50. All right. Now, I'm going to show you something very special that I can do that I bet none of you can do. Can any of you do that? Whoa, all of you can do that. All right. All right. Can you do this? Can you do this? Wow, I thought I was special. If we pretend our hand is a CPU, it's a simple CPU. Well, actually, I say it's a simple CPU, but the human hand is amazing, right? But we'll call it a simple CPU for this example. You know, there are things that we can all do with our hand, and individual things are not that interesting. None of you are going to go brag to your parents that, oh my gosh, my professor can do this. Okay? It'll be even worse when you say, oh, I can do this. But when you're like, when you're 4 months old and you discover your hands, parents are thrilled. It's like, oh my gosh, look, he's grabbing. It's so amazing, right? I'm still amazed by it today. Okay, but we have these little tiny little things that we can do with our hand. But those things in and of themselves are relatively useless, right? It's when we put those movements together in a sequence that allows us to accomplish the human idea of a task, right? This goes back to what Blade brought up. It's, what am I telling my computer to do? Well, I'm telling my elbow joint to extend. I'm even simplifying this, right? Then what am I doing? I'm telling my shoulder to move closer to this. Then what I'm doing, I'm telling it to, move a finger, then move another finger, then move another finger, then move another finger. Then I'm telling my thumb to move down and then move in. And then I'm telling one of my muscles, probably several of my muscles, to contract a little bit. And now I can say, now engage the shoulder muscle, shoulder joint, whatever, the muscle's lifting it, and now I can lift this up. That make sense? Any of those individual little tasks were not impressive in and of themselves. But when I performed a whole bunch of them in a row, I accomplished the human idea of a task. That is, pick up the bottle of soda. Make sense? That's what the CPU is. The CPU is this collection of little tasks, collection of little magic tricks. So you can think of this idea of wiggling your thumb as like a tiny little computer program created or written in hardware. You got your CPU, and inside there you have a whole bunch of logic gates and stuff like that. Stuff we'll talk about in 548. But you can think of them as a computer program written in hardware, okay? Now, this program right here is not as complex as pick your favorite video game, okay? But that doesn't mean it's not useful. So that CPU has this collection of hundreds of little tiny tasks that are generic in and of themselves, but if you call upon them in a certain order, they allow you to solve a problem. A human being might want to pick up the bottle of soda. And in order to tell a computer what you want, you can't just say, pick up the bottle of soda. If I'm talking to a human, I can, because there is intelligence on the other end, right? But if I'm talking to a computer, we don't have that intelligence. I have to say, perform this magic trick, then this magic trick, then this magic trick, then this magic trick, and you hope that the bottle doesn't fall out of your hand because you forgot to perform one of the magic tricks, right? Like, oh, I have it, and then you forget to contract the muscles and you just lift straight up. I didn't get it. I was right there. You didn't fully, unambiguously articulate the full solution to what it takes to pick up the bottle of soda. Why? Because we don't think about it like that. If I tell Blade to pick up his coffee mug, he just does it. You didn't think about all the little muscles you needed to do or anything, right? You just did it. Okay? So, oh look, now he's using intelligence. He's going to take a sip. I didn't even tell him to do that. He just decided, you know what, I need a sip. Is it water or is it coffee? Tea. Okay, that's acceptable. My wife tells me I need to drink more water. It's like I like water when I'm really thirsty, but I prefer basically anything else. It's very unhealthy. Yeah.
So I guess we will all heard of this term nowadays. People like advertising the neural network chips. So does they have any similarity to the old one, or have any difference?
Well, that goes back to your AI class, right? What does intelligence actually look like? So, you have neural network chips. What's a neural network? A neural network is a software model of how we think the human brain kind of works, right? So if you've trained it, so maybe you have a neural network and you've trained it on the task of picking up a bottle of water. I think that would be actually kind of difficult. The example I always use with neural networks is my first experience with it. was with back propagation using supervised learning, where I wrote a neural network, so I created it by hand. Today you would just use like TensorFlow or something like that, but this was before all that. So I wrote, and I think it was in probably C or probably C. I wrote a C program that represented a neural network, and decided, okay, well, I want to do multiplication with this. I want to kind of like second grade flashcards. I want to do my 1 through 10's multiplication table. 2 times 3, 2 times 4, 2 times 5, 3 times 3, 3 times 4, 3 times 5, so on and so forth. And what I did was I decided, okay, well, I'm going to represent my inputs in like binary format. All the way up to the number 10 can be represented in 4 bits? You need 3 bits to get you up to 7. You need 4 bits to get you up to 10. So my inputs were 8 total bits. 4 bits for my first number, 4 bits for my second number, and I decided I'm going to do multiplication. But instead of teaching it, instead of writing the steps to do multiplication, I knew the answer. So when I said 2 and 3, I expect a 6. So it ran through my neural network, it spit out its guess, and if the guess was wrong, you slap it on the wrist, you use the back propagation algorithm you're like tuning it, right? It's like tuning an instrument. You're like, I'll make this number a little different, I'll make this number a little different. The weights between the neurons, my simulation of the human brain. Okay, and I keep feeding it those inputs, making little adjustments every single time I get the answer wrong, until I have like this perfectly balanced neural network where I could feed it the 1 through 5's multiplication table and it gets them all right, or it gets many of them right. Sometimes you can't get them all right, but let's say got them all right. Then where I was fascinated, it's like a Frankenstein type thing, is I then fed it the 6 through 10's table, data it had never seen before. And it got almost all of them right. Because I had created, quote, intelligence, right? I created through my intelligence something that had captured the underlying pattern of multiplication. So the magic trick that neural network did, if we replace that little computer program on the CPU that does this, we replace that with a little neural network that ultimately accomplishes that, right? But maybe the neural network actually accomplishes this, the grabbing or something, maybe it does a little bit more, whatever, it doesn't matter. All I've done is I've replaced the normal algorithmic approach of this with a neural network that says, oh, you give me the right inputs, I'll still do this. My output is the same. The way I arrived at that output is different. Does that make sense? That doesn't mean they can't be more powerful, but it's an alternative approach to describing certain problems, because some problems, we take a CPU that might have a bunch of neural networks in them, some problems can be better expressed, or maybe even can only be expressed through a neural network. If we take a larger problem that we've already referenced today, like teaching a robot to walk, right? How do you do that? Well, maybe it has a neural network and it's going to keep falling over, right? So first, maybe you try to train it to balance itself. And what are you doing? Well, you apply forces to it and it starts falling over and it catches itself. You tune the network until it can always catch itself. It doesn't matter what you do, it can keep its balance. You don't know how it's doing that. It's just firing all of its different servos and stuff like that until it doesn't fall over. Then you start teaching it to naturally start falling over, but catch itself, and catch itself, and catch itself. And now you taught it to walk. It's learned the pattern of walking, rather than us having to describe to it all the steps it should take to walk. Both of them are potentially viable solutions to that problem. But if we say that walking is more complicated, it's too complicated for human beings to be able to articulate how it's done. We might say that a neural network that has been specifically trained to capture the pattern of, maybe it's the full thing of walking, maybe it's just how the knee joint works, maybe it's how the ankle works, whatever. You can have multiple neural networks working together, but instead of a human being being reliant on explaining every little step, instead, through trial and error, we've created a pod that operates as the solution to something, even if we can look at that and say this is a black box. We don't understand why this solution works, it just does. Because we've trained it on a bunch of data and it's learned to work. Does that make sense? So don't necessarily, and I'm sure this is compatible with what you just had in your AI class, don't necessarily consider a working neural network as true intelligence. It's an alternative solution to a problem that we may or may not have been able to articulate ourselves. That's what's so exciting about neural networks, about the idea of artificial intelligence. It's okay for us to say, well, we really want to have perfect intelligence, right? We want to have human-like intelligence. It's okay for us to dream for that. We can even hope that it's possible. And effectively we're playing the role of God then. I don't know if it's possible or not. I mean, God made us. But the point is that it doesn't matter whether it's possible. We can dream for that, but at the very least, we can fake intelligence. We can create artificial intelligence, solving little problems that we maybe would have trouble articulating through a normal programming language. But we've decided that, this is still a problem we want to be able to solve. So when you solve a problem, you want to use the right tool for the job. And you might decide that a normal programming language will not allow me to solve this problem, or would be very, very difficult, or I don't even know where to start, whatever it is. But maybe you say, you know what? A neural network, I wonder if this could be effective in this. I wonder. And that's where you start getting into problem solvings with alternative approaches to problem solvings that are outside of a human being giving a whole series of instructions. Because again, we don't need to know how the car actually works. We just appreciate that it does work and we can drive it. Make sense? Okay. So anyways, what's our CPU? It's this collection of magic tricks that ultimately allows us to solve problems. And the job of us is to ultimately somehow deliver to our CPU a set of instructions that we want to accomplish in a certain order. Do 1, then 2, then 3, then 4, and you've picked up the soda bottle, right? But we don't want to drop down to that CPU's level. We don't want to say, perform magic trick 00110111. Now do magic trick 01110111. Now do magic trick. We would go insane very quickly. A little 2-button keyboard. We don't want the 2-button keyboard, right? So, I mean, it would make our computers more compact if we only had the 2-button keyboard, but not really for human consumption. That's not our way of doing things. So instead, we want to be able to say, pick up soda bottle, and something under the hood to translate that into the 15 instructions that are required in binary to accomplish that. Make sense? Human beings give the 99% of the power, the computer has 1% of the power, right? Ultimately, the tool turns it into zeros and ones, but that tool is doing a lot of work for us in the middle. Make sense? So from this class's perspective, the relationship we have with the CPU is ultimately the guy doing the work. But we are going to use a series of tools that live between us and the CPU so that we don't have to worry about the CPU too much. But instead, we are going to be using some of these other tools to ultimately translate our desires down to those steps. Okay? So, in here, I've promised that we're going to be writing a programming language. What does that mean? Well, you can think of programming language as the same thing as a natural language. We're going to have to first create a syntax. This is the stuff I want to say. Now, most of us who have had programming before have worked with common languages that are based off of the C programming language, right? So you have if statements, you have for loops, you have while loops, you have, the idea of return types and function names and stuff like that. Now, realistically, since we're going to be approaching this from a programmer's perspective, we're going to have the same stuff. But what our goal in here is going to be is we're going to be developing a programming language kind of meant for a beginning programmer. All right, because even when we think about the C programming language, if you've dealt with anything based on that, so C++, Java, C#, Swift, basically any programming language that's modern is based off of C at some level, okay? We have expectations as programmers related to that. But what I want to do is I want to build a tool kind of around this idea of, oh, I need to remember something. And oh, I want to ask a question. And oh, I want to repeat something some number of times. So something that is maybe a little bit more understandable to a person. If we take everything I've talked about today in that context of what are these languages actually doing? When we're walking down the hall and not falling over, we're asking questions of what are we actually doing? Make some sense? Okay, so the idea is we're going to pick a syntax that's purposely different than C, so that we don't fall into the habit of saying, well, I'm going to use the same syntax as an if statement and then under the hood implement it as an if statement. We will be implementing it as an if statement, but we want to have that forced difference so that we feel like, oh, I'm translating this sentence, this description, into the things on the other side that need to accomplish something. Make sense? Okay, so we're going to be picking a syntax that our human programmers are going to be using. That's what, when they write software in our language, it's going to be using this syntax. Make sense? Okay. Now we ultimately then need to parse that syntax into chunks that our interpreter we're going to write in here. We're going to write an interpreter because we want to leave the really low level stuff out right now. Okay. There's another course in the computer science, the software engineering specialization concentration in our major called compilers. Okay, and I teach that class as well. Compilers are going to kind of take the same starting point, but we're going to be we're going to be doing the job of not the programming language itself. We're going to be doing the job of taking a language that already exists and turning it into those zeros and ones. And you're going to see how much more difficult that is. Because what you're going to see is in an 8-week course, we're going to have a very simple compiler that can't do that much. Make sense? Okay. Maybe at the end, we've trained our CPU to pick up the soda bottle. That's kind of it. And then you think about how amazing languages like C, C++, these things are. It's also evidenced by, for those of you who have programmed often, how long ago did C come out? Yeah, I think 1968, something like that. Long time ago. Okay. Then we had C++. Late 70s. Yep. Then what was next? Java. When did Java come out? No, it's like 93. Yeah, I think like 93, something like that. I think Java became something that people could develop in like right around 1993, 1994. That's when I first started. I started using Java whenever it came out. So something in the early 90s. Then what about C#? Yeah, like earlier than that. Yeah, C# was kind of right around 2000. Because that was after when Microsoft got sued by Sun Microsystems, blah, blah, blah. So, and then what was after C#, what was the next compiled language that came out? Swift. When did Swift come out? Even later than that. Yeah, like not long ago, right? Swift. So you notice in there as we went through that, we have these huge gaps of time between when each of those languages came out, with the closest gap being Java and C#, which the only reason that gap existed, that the shorter gap existed, is because of a lawsuit, right? Microsoft was perfectly happy just stealing Java. Nothing's wrong with Java, right? We're good, no problem. Okay, a lawsuit caused them to delay it. So with all that in mind, really what you're looking at there is you have like 5 high-level languages. We had Objective-C back there as well that kind of branched off of C kind of in the late 70s as well. Microsoft went with the C++ route. Apple went with the Objective-C route because they can't agree with anything, right? The rest is history. But you know, the punchline there is that when you take compiled languages like that, they must be complex to create. When we look at the last 50 years and see how few of them have come out, right? 5. In that same 50-year period, how many interpreted languages have come out? How many interpreted languages, so interpreted being like Perl, Python, PHP, JavaScript, you know, how many interpreted languages do you think were invented in the last year? More than 5 in the last year, right? Because interpreted languages are much easier to write because what they do is they use the foundation of a compiled language to create an interpreter that translates a parsed syntax into zeros and ones, and those zeros and ones are ultimately created using a compiler that's already been built. Make sense? So we don't have to build that tool. And the compiler's course will learn what it would take to build that tool, and we'll recognize that, oh, well, if it's not broken, maybe we don't want to fix it. If a C-based language already pretty much does what it needs to do, maybe we don't want to fix it. In fact, I'm of the belief we didn't need Swift. Right? Swift exists to try to get people from the Java side to come over to do iOS and Apple development, because it looks a lot more like Java than it looks like Objective-C. The Objective-C developers were not complaining that Objective-C was too old. Objective-C developers were perfectly happy with the Objective-C programming language. In fact, to this day, it's one of my favorite languages. To this day, I probably prefer Objective-C over almost any other language. I just like the expressiveness of it. It's just one of my favorite languages. Sure.
Does Objective-C, does Swift has its own compiler?
Yeah.
What I always thought is all those languages also using kind of the C compiler.
Well, it's possible they base themselves off the C compiler, but they do anything that boils down to native code is going to have a compiler involved. Now, is it possible they used the C compiler as a starting point and kind of, you know, get 30% of the job done? It is possible, but there are aspects of that compiler that are built specifically by Swift, because Swift promises all these performance benefits that didn't exist in C and stuff like that. So certainly it's its own compiler that maybe has taken some stuff from older compilers. But you know, I think Swift is kind of just like a ridiculous language. I think it's completely idiotic. The fact that you can name variables with emojis.
That makes sense, but normal people.
Yeah, right, because now we have this new language of emojis, right? Isn't it funny how history repeats itself? We look at natural languages. You go back to the Egyptians, right? And you know, on the walls of the pyramids, what do we have? We have hieroglyphics. Hieroglyphics are little picture things, right? And then we get to these natural languages like English, and now we're right back to hieroglyphics. We replaced our normal natural language with pictures again. So it's kind of funny. But I get why Apple did what they did with Swift. And I've written code in Swift. It's fine. I mean, there are some perks to languages that force you to unwrap variables and make sure you don't get null pointer exceptions and stuff like that. So some of the things make some sense, but I don't know, just we didn't need it. If you're an Apple developer, you're perfectly happy with Objective-C. You know, it was fine. It was fine. It did what it needed to do. So in any case, we're going to pick our syntax. We're going to build a parser that turns whatever our human-like syntax is into stuff that we can use inside of a programming language. Okay, then we're going to process that parse syntax using logic. That's usually called an interpreter. So we have a parser that turns it into kind of usable components. Then we have an interpreter that then takes those usable components and does something with them. And ultimately we have logic that the computer can directly run, and that's going to be for us done by the compiler that we didn't write, somebody else's compiler. Makes sense? In this case, the compiler for the Java language, which is sort of an interpreted language. So we have another interpreter that's going to be involved here that we didn't write either. That's okay. We're using some other tools to be able to explore the structures of a programming language using Java. Make some sense? Okay, so what I want to do for the remaining time here, because our homework assignment for next class is going to be to create a project in, we're going to just do Hello World, right? Little Hello World program in Java. Because the proof is, what I want to know from you on Wednesday is that you're able to do your homework, right? That is, you can write some code and you can get it up on GitHub and you can submit to me a link. Make sense? So what I'm going to do in the next couple of minutes is I'm going to create a project in Eclipse and release it to GitHub. So I'm going to show you the whole process. Okay? Now, we have this thing called Git Desktop. GitHub. So this is a program that I've already linked on Blackboard, and it was also in that thing I sent you yesterday. So you'll want to download GitHub Desktop. If you've already worked with GitHub before and you have another way you want to interface with it, that's fine. But I'm not going to manage 20 different GitHub approaches. I've done all the command line GitHub crap and stuff like that, but I'm going to expect that you're going to do it the way I'm going to do it now. If you want to do it alternately, that's fine, as long as I end up with a link. Okay, make sense? So download GitHub Desktop, also download Eclipse. Eclipse being our Java development environment. Okay, so once you have both of those on your computer, the first thing you're going to do is you're going to open up GitHub Desktop. Okay, and what I'm going to do here is, with GitHub Desktop open, I'm going to create a new repository. All right, and I'm going to choose what I want this repository to be called. I'm going to call this guy CSC549 repo1. Okay, actually let's call it a test repo. All right, now it's going to ask me where I want to store this guy. So I'm going to actually put it in a little bit different place here, just because I don't want this isn't going to be a long-term thing. So I'm going to store it in my downloads folder. Okay, now what this is going to do is it's going to create basically an empty folder for me with some tools that are hidden from me in there to manage this repository. And we'll talk more about what that means as we kind of go farther into GitHub, but we won't go too deep into GitHub. This is more going to be just the mechanism that we interface with this thing. All right, so I wanted to create a folder called CSC549 test repo for me in my downloads folder. That's what this is going to do. Okay, now I'm not going to initialize it with a README. It's not required. I'm not going to use any git ignore or license. So that's all you need to do initially. So I'm going to go ahead and say create repository. Go ahead. Git ignore is for the best use. Best example I can give you is with like Unity. If you write like a video game, if you've ever written something in Unity, it ends up, the source for it is this gigantic thing, because Unity's doing all of this stuff behind the scenes. Where you can tell with git ignore, there's a whole bunch of patterns already. One of them is called Unity, where it knows the collection of 70 file types that it should not put into the repository, right? So it automatically manages that for you, so that when you commit your code and ultimately send it up to the cloud, it only sends the code that needs to be there, because Unity, the tool, will rebuild those other files automatically. Make sense? So that's what git ignore does, is it says, hey, here's the kind of files we don't actually need to store because it's, they'll be rebuilt by the tool. All right, but in this case, I'm not doing any of that. All right, so now what I have here, if you notice here under my downloads, I have a new folder that was created for me. Okay, so now I'm going to go into Eclipse. This one? Oh. So I'll go into Eclipse here. I'm going to close all these files. It's from something else. All right, so over here on the left, I have my package explorer. Yours will probably be empty when you first download this. So I'm going to come out over here. I'm going to right click. I'm going to create a new Java project. And I'll call this guy CSC549 test project. Okay. All the other stuff you should be able to leave alone except this default location. I want to store this inside of that folder that my repository just got created. So I'm going to unclick this. I'm going to click Browse. I'm going to go to Downloads. I'm guessing it's at the very end, or do I have to just search for it? No, it doesn't show up first. So I'm going to, this is like a weird bug in the OS. So it's called CSC549 test repo. CSC549, there's my test repo. So I'm going to say, I'm going to store this project inside of that folder. Okay, so my project name is this, I'm storing it inside of that folder. Okay, now you're going to want to pay attention to this next part carefully because this is something with the newer version of Eclipse. Java now uses something called modules, which I don't use. So we're gonna ignore something here in a second, but it's an important thing for you to pay attention to as I do it. All right, so only thing that's important to us here is that we name it and we put it inside the folder we just created. So I'm gonna go ahead and hit finish. And notice it wants to create this module thing. I'm just gonna say don't create. Okay, so now I have a project here called CSC549. And it has a folder in it called source and nothing in that folder. So I'm going to right click on source. I'm going to create a new class. All right, and I'm going to name this class driver. Doesn't matter what you call it, just name it driver. This is going to be our hello world program. So I'll say public static void main. All right, so there's our hello world program. And then I'm gonna just test it, make sure it works. I'll hit this play button, and there down here is our hello world. Ha, working hello world program, great. All right, nothing too impressive, but if you just copy my syntax here, this will make it work as hello world. Remember, Java is case sensitive. All right, so now we're done with the coding side of it. I'm gonna go back over to Git Desktop. And notice that I have some new files, okay? So what I want to do is I want to commit these changes because inside of that folder, the Git tool, Git, maintains some information about your files and how they've changed over time and stuff like that. So I'm going to commit these changes. So I'm going to say, we'll call this guy initial commit. And then I'll just say commit to main. Now, all I've done here so far is I've updated my local repository, this folder that lives on my computer. Now, in order for us to submit our homework, though, we need to get it to the cloud. All right, so somewhere, you're going to go to GitHub. And if you haven't already done so, create an account here on GitHub. If you use your .edu email address, you get a free professional account where you can create private repositories on there, which is what professionals would use to keep their code and not let other people see it. But any repository you create for my class, make public so I can see it. All right, and you'll see that here in a second. So I'm telling you another thing to pay attention to. All right, now you'll need to one time go into GitHub Desktop and go to, I think it's in Preferences, and you'll have to set up your account. You'll sign in to GitHub. Okay, I've already done that, okay, on mine, but you'll have to sign into GitHub the first time, and then it'll just remember it. All right, so what I want to do now is I want to publish this repository. And it's going to have a name, okay, so that's the name of it. Make sure you uncheck this box that says keep this code private. And then say publish the repository. So what this is doing is it's creating that repository on my GitHub account in the cloud at github.com. So now if I go back to github.com, I just refresh this, I'll see now that I have, where's my latest CSC549. So here's my test repo that was created there for me. So I want you to submit this link, the link to the test repo. That's what you're submitting for your homework assignment. So I can click on it and see your code. And I should be able to view this as a public repository and see the code you wrote. All right, so notice it has this stuff in here with source, all this jazz. Here's my driver.java, that stuff. Now, just as an example, the last working piece of GitHub, you don't need to do this part. What you need to do for your homework is identical to what I just did. But just to show you the premise here for GitHub is I can come back in here and I can say, well, I'm going to add a couple of exclamation points to my hello world. Okay? I changed my program. Now, when I go back to GitHub Desktop, notice it notices that change. I'm going to go ahead and I'm going to commit that change. And all that did is commit it locally. If I want the change to now be in the cloud, I have to push it. So I push it. Now it's up on the cloud. I go back here and I refresh this. Notice it has my new code. Make sense? So for your homework assignment, create a Hello World program, get it up into GitHub Cloud, and submit a link to that I can click on and see your public repository with your Hello World code in it. Make sense? Basically follow the last 10 minutes of this video. There'll be a link to this video up on on Blackboard. Questions, comments, concerns, bribes? Go ahead. Under Blackboard. There'll be an assignment on Blackboard I'll put up today that'll be called on homework assignment 1, something like that. And you'll submit to that your link to get your GitHub project. You don't have to, but if you do that, you get like a professional version of a GitHub account without paying for it. Because they want people in education to use it so that when you go and work for a company, you say, oh, I'm already used to using it, and then the company gives GitHub money. That's the premise. But you might as well get private repositories from it. But the caveat there for me is I want you to have the better account for free, but make sure you make the repositories you submit to me public. Otherwise, I won't be able to open it. Make sense? Okay, I will see everybody on Wednesday, same time, same station. We'll meet in this room unless we have another problem. Looks like I just have enough battery life, so I'm going to have to cut this off now so it starts processing the video. But I will see everybody on Wednesday. Yeah, I see that. What's this?
I was having few quick questions.
Yep.
One question was for the test, do we have to download some software, something like that, for the final exams?
Probably not, but we can deal with that once we get closer to it, when I've actually thought about what the exam looks like.
Okay.
All right?
Thanks.
All right. I will see everybody on Wednesday.